For as long as humanity has looked up at the stars, one question has echoed across time: are we alone in the universe? This simple yet profound query stirs a sense of wonder in our hearts and ignites the very essence of our curiosity. A question that, though centuries old, still haunts the minds of thinkers, philosophers, and scientists alike. And yet, despite the incredible advancements we've made in our exploration of the cosmos, this question remains unanswered. Long before we had telescopes to peer into the depths of space, humans looked up with wonder. The ancient Egyptians, Babylonians, and Greeks saw the stars as gods or omens, mysteries to be revered and pondered. Early astronomers like Aristotle and Copernicus dreamt of a universe far greater than the one their eyes could see. But still, the question remained, is there life out there? And if so, what does it look like? As we advanced through the ages, the question shifted from myth to science. In the early 1600s, Galileo Galilei turned his telescope to the skies and saw the universe in a way never before imagined. The stars were not distant gods but worlds, each one a sun in its own right, with planets of their own. Yet even then, the question remained, could any of these distant worlds harbour life? Fast forward to the 20th century, and the dawn of space exploration finally allowed us to answer some of these ancient questions. In 1965, humanity sent its first probe to the red planet, Mars. And in 1976, Viking 1 looked for signs of life in Mars's soil. We found none, yet the question persisted. Could life exist in the depths of the solar system, in places far beyond the familiar boundaries of Earth? It wasn't until the early 21st century that the search for life took a monumental leap forward. With the launch of NASA's Kepler Space Telescope in 2009, we began to truly understand the vastness of the universe. Kepler's mission was simple yet profound: to find planets outside our solar system, planets that orbit other stars, planets that might resemble Earth in size and composition. These worlds, known as exoplanets, might just hold the answers to our greatest question, and Kepler did not disappoint. In its 9 years of service, the telescope discovered over 2,600 confirmed exoplanets, planets that exist in the so-called habitable zone, the sweet spot around stars where liquid water could exist. The key ingredient for life as we know it. But finding a planet that could host life is one thing. The next question is far more complex. What kind of life could thrive there? What does life need to begin? Could it be similar to the life we know, or could it take on entirely different forms, perhaps beyond our current imagination? We know that life on Earth thrives in environments that seem inhospitable. Deep beneath the ocean, in acidic hot springs, in frozen tundras, and even in boiling vents on the ocean floor. Extremophiles, as we call them, are organisms that not only survive but thrive in these extreme conditions. What if life elsewhere in the universe has adapted to environments just as extreme, or even more alien to us than we can fathom? This is the concept of life beyond Earth, not just life as we know it, but life in forms we haven't yet imagined, existing in places we never thought possible. Consider Titan, Saturn's largest moon, a place so cold and alien that most people wouldn't even think of it as a candidate for life. Yet Titan is a world of extraordinary interest to scientists. Its thick, nitrogen-rich atmosphere and lakes of liquid methane tell us that Titan, despite its harsh conditions, is far more Earth-like than we initially thought. In 2004, NASA's Cassini spacecraft and its Huygens probe captured images of Titan's surface, revealing riverbeds, mountains, and valleys, all shaped by liquid flows. But these aren't rivers of water, they're rivers of methane, a liquid at Titan's frigid temperatures. Could life here be based on methane instead of water? Could these strange rivers support forms of life that are unimaginable to us? It's a thought that stirs the imagination. Life, not as we know it, but as we might one day come to understand it. Mars, our closest neighbor, is also a world full of mystery. Evidence suggests that billions of years ago, Mars may have had rivers, lakes, and even an ocean. The Curiosity rover, still exploring the planet's surface, recently uncovered evidence that water may have flowed freely across the Martian landscape. But where did it go? And could Mars, with its dry deserts and frigid surface, still harbor traces of ancient life? Or is it possible that life once existed here and disappeared long ago, leaving only fossils, whispers of a lost time? The search for life, however, is not confined to the planets within our solar system. The discovery of exoplanets has opened up an entire galaxy of possibilities. Our Milky Way alone is home to hundreds of billions of stars, many of them hosting planets, and these planets may be orbiting in the habitable zones of their stars, places where liquid water could exist, where life could emerge. So what does it mean to search for life? What are we really looking for when we peer into the dark vastness of space? Perhaps the search for life is not just about finding extraterrestrial beings. Perhaps it's about finding a deeper connection to the universe itself, about realizing that we too are a part of something much larger, a cosmos that stretches far beyond the stars we see tonight. We are closer than ever to answering this great question. Our telescopes are more powerful, our probes more capable, and our understanding of the universe is growing every day. But the question still remains, are we truly alone in the universe? Will the next discovery be the one that unlocks the answer? Will it come from a distant exoplanet or a moon in our own solar system? The search continues, and with each new discovery, the mystery grows. Each step brings us closer to the stars, closer to the answer we've been seeking since we first gazed at the night sky. Perhaps one day we will no longer ask, are we alone? But rather, who else is out there waiting to meet us? Until then, the question remains, and the journey continues. The universe is vast, filled with billions of stars and an untold number of planets, each one a silent witness to the passage of time. For centuries, we've gazed up at the night sky, knowing that somewhere beyond the stars, there is something more. But what? Could there be life out there waiting to be discovered? This question, are we alone in the universe, has reverberated through the hearts and minds of humanity for millennia. It's a question that stirs wonder, fear, and excitement all at once. It has guided the musings of philosophers and the dreams of astronomers alike. But in all this time, the answer has remained just out of reach. Until now. The story of our search for life beyond Earth is not just a story of telescopes and rockets. It's a story of our longing, our insatiable curiosity to know our place in the cosmos. It's a tale that begins long before the first space probe was launched. In fact, it dates back to the very beginning of civilization, when the ancient Babylonians, Greeks, and Egyptians looked up and saw the stars as gods or signs of the divine. They asked themselves, is there life beyond this world? In the 16th century, astronomers like Nicholas Copernicus and Johannes Kepler shifted our understanding of the heavens. They revealed that Earth was not the center of the universe, but a small planet orbiting the sun. A humbling realization. And yet, even with this newfound perspective, the question remained, could life exist elsewhere? It wasn't until the 20th century that we truly began to answer that age-old question. With the dawn of space exploration, humanity finally began to venture beyond Earth's atmosphere, sending probes and spacecraft to explore distant worlds. The early space missions of the 1960s and 70s, like the Mariner and Viking probes, turned our attention to Mars, the most Earth-like planet in our solar system. Could the perhaps be traces of life on Mars, or at least signs of past life? The Viking missions in 1976 were a turning point. For the first time, we sent a spacecraft to land on the Martian surface and analyze the soil for signs of life. The results were inconclusive, and many scientists believed that Mars had no life, at least not in the way we understand it. But that did not deter us. It only deepened the mystery. And then, in 1995, something remarkable happened. An astronomer named Michel Mayor and his colleague Didier Queloz discovered the first exoplanet, a planet orbiting a star outside our solar system. The discovery was groundbreaking. Up until that moment, we had only known of the planets in our solar system. But now we had evidence that other stars, many of which could be billions of light years away, had their own planets. And where there are planets, could there not also be the possibility of life? This discovery opened the floodgates. Soon, astronomers discovered that there were not just a handful of exoplanets, but thousands, millions even, scattered across the galaxy. These worlds were diverse, some hot and desolate, others cold and distant, but some were just right, located in what we call the habitable zone, the region around a star where liquid water could exist. The habitable zone, it's the sweet spot, the place where life as we know it could potentially thrive. But water alone is not enough. We also need the right chemical ingredients: carbon, nitrogen, oxygen. These elements, the building blocks of life, are ubiquitous throughout the universe. In fact, recent research has shown that some of the most common molecules in space, things like methane and ammonia, could form the building blocks of life. But even as we explore these distant exoplanets, we must ask, what if life isn't exactly like ours? What if it exists in forms we can't even imagine? Could life survive in extreme environments unlike anything we've experienced here on Earth? On our planet, we've discovered extremophiles, creatures that thrive in environments that would seem impossible for life to survive. From the boiling vents at the bottom of the ocean to the frozen tundras of Antarctica, life finds a way. What if life on other worlds exists in forms we can't even fathom? What if it's based on methane or some other exotic solvent? Or perhaps life doesn't even need to rely on carbon, nitrogen, and oxygen in the way we understand it. As our understanding of life itself expands, so too does our sense of wonder. If life can thrive in such extreme conditions on Earth, could it not also find a way to exist on a distant exoplanet, perhaps orbiting a star much older or younger than our own? In our search for life, we must also consider the possibility that we are not the only ones looking. For decades, scientists have been scanning the skies for signals, for any indication that another civilization has reached out across the stars. The search for extraterrestrial intelligence, or SETI, listens for radio signals from distant worlds. And yet, despite decades of listening, we have yet to hear anything. Are we truly alone in the universe? Or are we simply too early to detect the faint whispers of life that might be out there? Perhaps the next generation of telescopes and space probes will bring us closer to the answer. In the meantime, we continue to search, to listen, to explore. The discovery of exoplanets is more than just a scientific breakthrough. It is a glimpse into the vast potential of the universe. It tells us that we are not alone in the void, that there are countless worlds out there, here, waiting to be explored, and perhaps, just perhaps, one of these worlds will reveal the answers we seek. The universe is a vast canvas, one that is still being painted, piece by piece, with each new discovery. The more we learn, the more we realize just how much we don't yet know. Each star, each planet, holds a mystery, a story waiting to unfold. Where will the next discovery take us? Will it come from a distant exoplanet light years away, or from the icy moons of our own solar system? Will we find life within our reach, or will the search continue for generations to come? The cosmos has awakened, and as we reach out toward the stars, we can only wonder, what secrets does it hold? What discoveries await us just beyond the horizon? Could it be that somewhere in the quiet depths of the cosmos, a world exists that mirrors our own? Could life, as fragile and miraculous as it is on Earth, have found a home elsewhere? For centuries we have asked this question, gazing at the stars, wondering if the twinkling lights above are solitary, or if each one harbors secrets waiting to be discovered. The search for other worlds, planets beyond our solar system, was once a dream that seemed impossible. Before the 1990s, astronomers could only speculate. We observed distant stars, but the planets that might orbit them remained invisible, cloaked by their stars' brilliant glare. And yet the possibility that our universe might teem with planets, perhaps even worlds like our own, persisted in the imaginations of scientists and dreamers alike. Then in 1995, the unimaginable became real. Michel Mayor and Didier Queloz detected the first confirmed exoplanet orbiting a sun-like star. It was a gas giant, massive and unlike anything in our solar system, but it was proof planets do exist around other stars. And with that discovery, the cosmos felt suddenly closer, more intimate, and infinitely more intriguing. Yet the real revolution came in 2009 when NASA launched the Kepler Space Telescope. Kepler was a sentinel in the dark, a voyager designed to scan distant stars for the faintest dips in brightness, a subtle signal that a planet might be passing in front. This mission, simple in concept yet extraordinary in execution, opened the door to an entirely new understanding of the universe. Kepler's findings were astonishing. Within months, astronomers were uncovering thousands of exoplanets, worlds of fire and ice, gas giants larger than Jupiter, and rocky planets smaller than Earth, each orbiting stars hundreds, even thousands of light years away. And among them, a precious few were identified as potentially habitable, orbiting their stars at just the right distance for liquid water to exist. Consider this, a planet not too hot, not too cold, where water, the fundamental ingredient of life as we know it, could flow freely across its surface. These were the Goldilocks worlds, and Kepler found them by the dozen, then the hundreds. Our galaxy, it seems, is not just vast, it is abundant. There are more planets than stars, more worlds than we ever imagined, scattered across the Milky Way like pearls on a cosmic string. And yet numbers alone cannot capture the wonder. Take Kepler 452b, often called Earth's cousin. This world orbits a star remarkably similar to our Sun, and it resides in the habitable zone where liquid water could exist. We do not yet know if it has oceans, rivers, or life, but the thought is tantalizing. Could a sunset there mirror the golden hues we see on Earth? Could winds stir the surface in ways both familiar and alien? Or imagine Kepler 186f, a world slightly larger than Earth, orbiting a red dwarf star. Its sky would look different, tinged with the reddish glow of its sun. Nights might last longer and the climate might feel alien to us, yet the basic ingredients for life may still be present. Even in these unfamiliar conditions, the potential for life persists, reminding us that our universe is far stranger and far more generous than we once believed. Our understanding of these distant worlds is still in its infancy. Telescopes can measure their size, their orbital period, and sometimes even the composition of their atmospheres. We can detect hints of clouds or the presence of water vapor. But seeing life itself, that remains a challenge for the next generation of explorers. And yet the very idea that life could exist beyond our planet has changed us, reshaped our imagination, and inspired a generation of scientists to look deeper. But the search for exoplanets is only one part of the story. We have learnt from our own solar system that life can thrive in the most unexpected places. Moons like Europa and Enceladus, icy worlds orbiting Jupiter and Saturn, hide oceans beneath their frozen surfaces. The Cassini mission revealed geysers of water shooting from Enceladus, and Europa Clipper is set to explore these oceans in the coming years. If these moons, cold and dark, can harbour life, what might we discover on the rocky exoplanets Kepler has revealed? The vastness of the galaxy can be daunting. Billions of stars, each with planets of their own, spinning silently through the cosmic night. Yet in this enormity lies hope. The odds suggest that life may not be rare, only distant. If life can emerge on Earth in the delicate balance of sunlight, water, and atmosphere, could it not also emerge elsewhere, given the nearly infinite opportunities presented by the universe? Consider the emotional weight of these discoveries. Each new exoplanet is a story waiting to be told. Each orbit mapped, each atmosphere analysed, is a brushstroke in a painting far larger than ourselves. And as our instruments grow more sophisticated, the James Webb Space Telescope, for example, capable of peering at exoplanet atmospheres in unprecedented detail, our ability to answer the most profound question of all grows ever closer. We may never find life exactly as we know it. Perhaps alien life is microbial, hidden beneath the ice of distant moons, or existing in chemical forms we cannot yet recognize. Perhaps it is intelligent, yet silent, existing in civilizations that have learned to traverse the stars in ways we cannot yet fathom. The possibilities are endless, and therein lies the magic of this search. The universe is not empty. It is a sea of planets teeming with potential, each one a spark of possibility. Kepler has shown us that our solar system is not unique, that Earth is not the lone stage upon which life can play. Across the Milky Way, countless worlds spin quietly, waiting for their stories to be discovered. As we gaze up at the night sky, we can feel both humbled and inspired, humbled by the enormity of what lies beyond, and inspired by the thought that life, fragile, wondrous and tenacious, may be waiting to greet us somewhere out there. Where will the next discovery take us? Will it be an exoplanet, bathed in the light of a distant sun, a moon hidden beneath ice, or an entirely unforeseen world we have yet to imagine? The answers remain unknown, but the journey itself, the act of searching, is transformative. The sea of planets stretches endlessly before us. Some may harbour life, some may not, but all remind us that we are part of something far greater than ourselves. In each new world, there is a chance to learn, to hope, and to imagine. And as our instruments grow sharper and our knowledge deeper, perhaps one day we will find the answer we have been searching for all along. Until then, we watch, we search, and we wonder. For in the vast ocean of the cosmos, every planet is a whisper, a promise, a possibility. And somewhere, perhaps life is waiting to say hello. What is life? Where did it come from? And could it exist somewhere beyond our pale blue dot? These are questions that have stirred humanity for centuries, whispered in the quiet of starlit nights and debated in the halls of philosophy. From the earliest civilizations to the scientists of today, we have asked ourselves, why does life exist at all, and how does it begin? For millennia, our understanding of life was shaped by myth and speculation. Some believed life was a gift of the gods, spontaneously appearing in the world. Others saw it as a delicate spark born of fire and water, earth and air. But as humanity's gaze turned from the heavens to the laboratory, the question of life's origin shifted from philosophy to science. Today, we know that life, in all its complexity, arises from simple building blocks: carbon, hydrogen, nitrogen, oxygen. These elements, common throughout the cosmos, can combine to form amino acids, nucleotides, and sugars. On Earth, these molecules are the alphabet of biology, forming the words and sentences of DNA and proteins that make life possible. In the 1950s, scientists Stanley Miller and Harold Urey conducted an experiment that would forever change our understanding of life's beginnings. By simulating the conditions of early Earth, a mixture of water, methane, ammonia, and hydrogen, energized by sparks of electricity, they were able to produce amino acids, the very molecules that form proteins. Life's ingredients, it seemed, could emerge naturally given the right conditions, but Earth is only one stage on which life might play. Could these chemical processes happen elsewhere, far from our sun? Could life emerge on a distant planet, under alien skies, in oceans of liquid methane or clouds of ammonia? Scientists now consider that possibility seriously. The universe is filled with worlds, some familiar, some wildly different, each offering the potential for life in ways we are only beginning to imagine. Consider the concept of extremophiles, organisms on Earth that survive, even thrive, in conditions once thought inhospitable. Microbes in the acidic pools of Yellowstone, bacteria beneath the frozen ice of Antarctica, life clinging to the walls of deep-sea hydrothermal vents, nourished only by chemical reactions. If life can endure these extremes here, what might it look like on worlds bathed in the orange haze of Titan, Saturn's largest moon, or beneath the icy crust of Europa, orbiting Jupiter? Titan is a world both alien and mesmerizing. Its surface is dotted with lakes and rivers, not of water but of liquid methane and ethane. Thick orange clouds hang overhead, and the landscape is sculpted by winds and tides unfamiliar to us. Yet, the chemistry of Titan is tantalizingly complex. Could prebiotic molecules, the precursors to life, form in such a place? Could life, radically different from our own, take root in these methane seas? Then there is Mars, our neighboring planet, cold and dry, yet etched with the scars of ancient rivers and lakes. The Curiosity rover has explored these ancient beds, analyzing rocks and sediments that may hold clues to the planet's watery past. Organic molecules once thought rare have been detected in Martian soil. Signs of past water, once a barren dream, are now undeniable. Mars whispers a question to us. If life arose there billions of years ago, could it still survive, hidden beneath the soil or in briny subsurface lakes? Another idea challenges our Earth-centric view even further: panspermia. Could life have travelled across the void, hitching a ride on comets, asteroids, or meteorites? Perhaps the seeds of life that sprouted here originated elsewhere, scattered across the cosmos like cosmic dust, waiting for the right moment to flourish. The idea is not mere fantasy. We have found amino acids in meteorites that have fallen to Earth. Life's building blocks, it seems, are universal. The cosmos itself may be a vast laboratory where life is continually attempted, tested, and refined. But even as we contemplate these possibilities, we must remember the subtlety of life's emergence. It is not merely chemistry, it is a delicate choreography, a balance of energy, matter, and time. The origin of life is as much about chance as it is about chemistry. On Earth, billions of years passed before the first self-replicating molecules emerged, before life gained the ability to adapt, to evolve, to flourish. Could similar processes occur elsewhere, independently, on distant worlds, under alien suns? As we look to the stars, we are not just searching for life, we are searching for a mirror, a reflection of ourselves perhaps, in the infinite variety of the cosmos. Every new discovery reminds us that life is not confined to a single path. It is adaptable, resilient, and astonishingly diverse. On Earth, the first living cells were simple, almost invisible, yet they carried the potential to build forests, oceans, cities, and civilizations. Could the same be happening elsewhere, in forms we cannot yet recognize? Even within our solar system, the possibilities expand. Enceladus, a tiny moon of Saturn, erupts with geysers that spew water into space. Beneath its icy crust lies a global ocean, warmed by tidal forces, rich in salts and organic molecules. Europa, its neighbor, hides a similar ocean, dark and vast, beneath a frozen shell. These oceans are bathed in the quiet energy of their planets, and though we cannot see them directly, they may harbor life in ways both simple and complex. The study of life's origins is, in many ways, a study of ourselves. It forces us to ask, what does it mean to be alive? To replicate, to metabolize, to respond to the world. And if life can emerge elsewhere, in environments utterly alien to our own, what might it teach us about the possibilities inherent in the universe? Could life be a universal phenomenon, arising whenever chemistry and energy meet in just the right way? Or is it a rare miracle, a singular event on this small blue planet? These questions may not have immediate answers, but the act of asking is transformative. With every discovery, every mission, every sample analyzed, we inch closer to understanding the tapestry of life. The universe is not merely a backdrop for our existence, it is an active participant, a stage on which life might appear, vanish, and reappear in countless forms, each telling a story we are only beginning to hear. The great oceans of Titan, the frozen seas of Europa, the ancient riverbeds of Mars, the building blocks scattered across comets and meteorites, all these pieces form a puzzle that is both scientific and poetic. Life's origin is not merely a question of chemistry, but a journey of imagination. It reminds us that the cosmos is not silent. It is humming with possibility, inviting us to explore, to wonder, and to dream. So we continue the search. We send probes, we peer through telescopes, we study extremophiles and meteorites, we simulate ancient conditions in laboratories. Each step is a note in a grand symphony of discovery, a gentle unfolding of the story of life. And as we ponder the origins of life on Earth, we are inevitably led to wonder about life beyond it. Where did life begin? Was it here on our fragile planet, or did it arrive from the stars? Could it arise independently on distant worlds, in oceans beneath ice, or in methane lakes under alien skies? We do not yet know, but the search itself is profound. In the quest to understand life, we uncover not only the secrets of the universe, but the depths of our own curiosity and imagination. Life is fragile, life is resilient, life is extraordinary. And as we explore its origins, we are reminded that the universe is full of possibilities, a cosmic garden where life may bloom in ways we cannot yet imagine. The question remains, where and when will we find it? Perhaps tomorrow, perhaps in a decade, perhaps on a world we have not yet dreamed of. And when we do, the story of life will expand beyond our wildest dreams, connecting us to a universe far more alive than we ever knew. The origins of life, a question without a final answer, a mystery that continues to invite us to explore, to imagine, and to wonder. And in that wonder, perhaps we find the true essence of life itself. What does it mean to survive where life seems impossible? Could life, even in its simplest forms, endure in worlds that defy everything we consider hospitable? These questions have haunted humanity since we first gazed at the night sky, wondering if the spark of life we know on Earth could ignite elsewhere. Our solar system, familiar yet mysterious, is not just a collection of planets orbiting a star. It is a gallery of extremes, worlds of ice and fire, of crushing pressures and blistering radiation, of oceans hidden beneath shells of frozen rock. To imagine life here is to stretch the boundaries of our understanding, to step beyond the familiar warmth of our home planet into the alien and the unknown. Let us begin with Titan, Saturn's largest moon, a world cloaked in a thick golden haze. Its skies shimmer with orange clouds, heavy with methane. On the surface lie lakes and rivers, not of water, but of liquid methane and ethane, glowing faintly under the weak sunlight that reaches this distant moon. Winds carve dunes of hydrocarbon sands, and the air smells, if it could be smelled, not of oxygen, but of chemicals alien and potent. Titan challenges everything we thought we knew about habitability. Water, the essential ingredient for life as we know it, is locked in ice here. Yet the chemistry of methane and ethane is rich, dynamic, and complex. Could life, entirely different from ours, arise in such conditions? Scientists speculate that life on Titan, if it exists, would not breathe oxygen, would not drink water, but might metabolize hydrocarbons, moving through liquid methane lakes in forms we can scarcely imagine. NASA's Cassini mission gifted humanity with glimpses of this alien world. It flew through Titan's thick atmosphere, analyzing the composition of its clouds and mapping its frozen surface. For the first time, we saw the curvature of methane seas, the patterns of rivers carved over eons, and the possibility of prebiotic chemistry at work. Titan is a laboratory, not of Earth, but of the universe's boundless potential. Travel a little farther, and we arrive at Europa, one of Jupiter's icy moons. Its surface is a frozen mosaic, cracked and crisscrossed with deep fissures, as if the moon itself were breathing beneath the crust. Beneath that frozen exterior lies a vast global ocean, kept liquid by the tidal forces of Jupiter's immense gravity. The ocean is dark, silent, and deep, perhaps home to life that thrives in the absence of sunlight. Europa reminds us that life does not require sunlight, that the energy to sustain it can come from the movement of tides, from chemical reactions deep in alien seas. Hydrothermal vents, similar to those on Earth's ocean floors, may exist here, spewing mineral-rich plumes into icy waters. On our planet, these vents teem with microbial life, surviving without the warmth of the sun, fed only by chemicals seeping from rocks. Could Europa host something similar? Could a moon, frozen on the outside, conceal a thriving world beneath? And then there is Enceladus, a smaller moon of Saturn, no larger than Arizona, yet extraordinary in its secrets. In 2005, Cassini observed plumes of water shooting into space from fractures near its south pole, geysers erupting through ice, carrying with them salts, organic molecules, and hints of energy beneath the surface. These plumes are not just scientific curiosities, they are invitations. They whisper of oceans warmed beneath icy shells, oceans that may be habitable, oceans that may, just may, host microbial life. Imagine standing on the surface of Enceladus, watching water vapor rise into the black sky, a frozen geyser against the backdrop of distant Saturn. The universe feels close in such moments, intimate, almost reachable. And in those plumes, we see the building blocks of life, scattered into space like cosmic seeds, reminding us that life may be more resilient, more daring than we ever imagined. These moons, harsh and frozen, challenge our definitions of life. They force us to ask difficult questions. If life can exist here, where extremes are the rule rather than the exception, what does that mean for the possibilities across the cosmos? Could planets orbiting other stars, hundreds or thousands of light years away, host oceans beneath ice, geysers, or exotic chemical seas? Could life flourish in forms so alien that we would not recognize it as life at first glance? Even closer to home, Mars teases us with the story of its past. Ancient riverbeds, dried lake beds, and minerals formed in water hint at a planet that was once warmer, wetter, and perhaps hospitable. The Curiosity rover has uncovered organic molecules embedded in Martian soil, fragile traces of carbon preserved for billions of years. Each discovery is a note in a symphony, a whisper from a world that may have hosted life, long before humans ever gazed at its red horizon. The common thread in these worlds is extreme conditions. Ice, methane, high radiation, crushing pressures. Life as we know it would struggle, perhaps perish in such environments. Yet life finds a way on Earth, clinging to the unlikeliest places. Deep-sea hydrothermal vents, acidic hot springs, the sub-zero waters beneath Antarctica's glaciers. Extremophiles teach us that life is adaptable, resilient, and astonishingly inventive. If it can survive here, why not there? In this cosmic perspective, the solar system is not barren, it is not lifeless, it is a canvas, painted with extreme environments that test the limits of biology and imagination. Each moon, each planet, is a potential stage for life, not identical to ours perhaps, but remarkable in its own right. Consider the emotional weight of these discoveries. When we send probes to distant worlds, we are reaching out across space and time, seeking answers to questions that define our existence. The data from Cassini, from Curiosity, from Hubble and future missions, all of it is a conversation with the universe asking, are we alone? Or is life in some form a cosmic inevitability? As we contemplate these frozen and harsh worlds, we are reminded of the fragility and resilience of life on Earth. The oceans, the forests, the deserts, all are delicate yet robust enough to sustain a remarkable diversity of forms. And yet, in the vast cold of space, beyond the protective embrace of our atmosphere, life may exist in ways that challenge our very understanding of biology, pushing us to imagine forms, metabolisms, and chemistries beyond the terrestrial paradigm. The harsh worlds of our solar system teach us humility. They remind us that life does not require comfort nor familiarity. It requires opportunity, energy, and chemistry, and the universe provides both in abundance. Titan, Europa, Enceladus, and Mars are not merely places to study. They are invitations to dream, to imagine, to ask the questions that have inspired generations of scientists, philosophers, and explorers. Where will the next discovery take us? Will we find life beneath Europa's ice, or drifting in Enceladus plumes? Will Titan's methane seas harbor forms we cannot yet envision? Perhaps life already exists, hidden in the cold, waiting for humanity to notice. Or perhaps it will arise independently in the future, proving that the universe itself is alive, patiently experimenting, endlessly creative. As we peer at these harsh worlds, we realize that the solar system is not empty. It is full of possibility, of hidden oceans, frozen landscapes, and alien chemistry. Each discovery deepens the mystery. Each mission expands the horizon of our imagination. And in the end, the search itself, the act of looking, of questioning, of dreaming, may be as profound as the disco, very of life itself. Life is tenacious, life is strange, life is waiting, and as we explore the harsh worlds of our solar system, we are reminded that the universe is not a silent, indifferent void. It is a living laboratory, offering clues, challenges, and wonders beyond our comprehension. Could water, that simple, clear liquid, hold the secrets of life beyond our world? Could the presence of water mark the line between lifeless rock and a living planet? For centuries, humanity has stared at the night sky and wondered, if life exists elsewhere, where would it find a home? Water is more than a substance. On Earth, it is the lifeblood of every organism, the silent thread weaving through ecosystems from the deepest oceans to the highest mountains. And yet, in the vastness of the cosmos, water is rare, not absent but hidden, concealed beneath ice, sand, and stone. To find it is to glimpse the possibility of life itself. Our search for water beyond Earth began with simple observation. Ancient astronomers noticed Mars's faint red hue and wondered whether its color hinted at something more than rock and dust. Could the red sands, streaked with dark lines, suggest the presence of water? For centuries it remained speculation, a question as tantalizing as it was elusive. The 20th century brought breakthroughs. Robotic explorers, guided by human curiosity, ventured into the silent expanse. NASA's Viking missions in the 1970s scoured the Martian surface, analyzing soil for traces of moisture and organic compounds. The results were inconclusive. Hints, whispers of water, but nothing definitive. Then, in the early 2000s, Mars Odyssey detected vast deposits of hydrogen beneath the surface, suggesting frozen water hidden just below the arid crust. Mars Express and later the Curiosity rover uncovered further evidence. Ancient riverbeds, lakebeds, and mineral formations that form only in the presence of water. These discoveries reshaped our understanding of the red planet. Mars was no longer a dry desert, once it was wet. Perhaps even it could still harbor water in hidden depths. But Mars is just the beginning. Beyond the asteroid belt lie the icy worlds of Jupiter and Saturn, moons that challenge everything we know about life and liquid water. Europa, with its cracked frozen crust, hides an ocean vast and dark beneath layers of ice. Tidal forces, generated by Jupiter's immense gravity, churn this ocean, creating energy and movement in a place without sunlight. Could life survive here, in liquid darkness, warmed by invisible currents? Saturn's moon Enceladus tells a similar story. In 2005, NASA's Cassini spacecraft detected plumes of water shooting into space, erupting from fractures near the South Pole. Within these icy jets were organic molecules, carbon, hydrogen, nitrogen, the very ingredients for life. These geysers are more than spectacular. They are windows into a subsurface ocean, a place where life, if it exists, might thrive in silence beneath the frozen surface. And then there is Titan, a world both familiar and alien. Its surface hosts lakes and rivers, not of water but of liquid methane and ethane. Yet beneath the icy crust, models suggest a layer of water mixed with ammonia, a hidden ocean, colder and stranger than any ocean on Earth, but potentially just as significant for the chemistry of life. Titan reminds us that liquid water, in combination with other chemicals, can exist in forms far beyond our imagination, challenging the very definition of habitability. These discoveries are not just about water, they are about potential, about possibility. Each ocean, each underground lake, each plume of water vapor is a thread in the tapestry of life across the cosmos. And here on Earth we see clues that life is resilient, adaptable, daring. Extremophiles, organisms that thrive in boiling hot springs, in the crushing depths of the ocean, in sub-zero ice, show us that life does not require comfort. It requires opportunity, energy, and chemistry. If it can survive here, why not there? The search for water is, in many ways, a search for ourselves. To understand where life could exist, we must first understand what life needs and what it can endure. Water is the starting point, the spark that transforms inert molecules into living systems. It shapes geology, drives climate, and nurtures ecosystems. Its presence, even in the smallest amounts, hints at the potential for life, a possibility that excites our imagination and challenges our science. Consider the instruments and missions that have made these discoveries possible. The Hubble Space Telescope glimpsed water vapor in the atmospheres of distant worlds. The Kepler mission revealed thousands of exoplanets, some within the so-called habitable zone where liquid water could exist. The Mars Reconnaissance Orbiter mapped ancient river valleys, and Curiosity drilled into rock to detect chemical fingerprints of past water activity. Each mission is a step forward, a piece of the puzzle, revealing the contours of worlds we have never touched, yet begin to know intimately. And still, the questions persist. Could there be lakes beneath the surface of Mars, hidden from view, waiting for discovery? Could Europa's ocean harbour microbial life in the darkness, forming ecosystems we cannot yet conceive? Could Enceladus's plumes carry life from a subsurface ocean into space, offering us a glimpse of biology beyond Earth? These are questions without easy answers, yet they are the questions that drive exploration, that push humanity to build rovers, landers, and orbiters. They push us to peer deeper into space, to listen for the faint signals of water, the whispers of life, the chemical fingerprints that suggest we are not alone. Water is a key, but it is not the only key. Energy, chemistry, and time are all essential components. Still, the discovery of water, in any form, transforms our understanding of the universe. It tells us where to look, where life might find a foothold, and where our next mission should journey. The presence of water is a promise, the promise that life in some form could exist, could emerge, could endure. The search for water is not just a scientific endeavor, it is a philosophical journey. It asks us to reconsider what we know about life, about resilience, and about our place in the cosmos. It challenges us to imagine forms of existence far removed from the warmth of our oceans and the light of our sun, yet fundamentally similar in their reliance on liquid, on chemistry, on the subtle balance of conditions that make life possible. As we scan the solar system, from the red deserts of Mars to the icy moons of Jupiter and Saturn, we begin to see a pattern, a hint that life may be more common, more persistent, more inventive than we dared to imagine. Europa, Enceladus, Titan, and Mars are not barren. They are laboratories of possibility, inviting us to ask the same questions our ancestors asked when they first looked up at the night sky. Are we alone, or is the universe teeming with hidden oceans waiting to be discovered? Where will the next discovery take us? Will we find subsurface lakes beneath Mars' frozen soil? Will we glimpse life in the plumes of Enceladus? Will Titan reveal oceans beneath ice, where chemistry is alive and dynamic, yet entirely alien? Each discovery will reshape our understanding of the cosmos, our understanding of life, and our understanding of ourselves. The search for water is the search for life's possibilities. It is a journey across space and time, a quest for the hidden, the frozen, the unseen. And as we explore, we are reminded that the universe is not silent, not indifferent. It is a living laboratory, a canvas painted with oceans beneath ice, rivers carved in rock, and clouds heavy with vapor. Each discovery brings us closer to the profound truth. Life is not confined to Earth. It may exist anywhere. The universe whispers the right conditions. Anywhere water flows, even in secret, waiting for discovery. The search continues. For every plume of water, for every hidden lake, for every glimmer of moisture on a distant world, we inch closer to an answer that has eluded humanity for millennia. Where there is water, there may be life. Where there is life, there is a connection, a reminder that in the vast expanse of space, we are not merely observers. We are participants in a universe alive with possibility. And so we look outward toward the red sands of Mars, the icy moons of Jupiter, the methane seas of Titan. We imagine what life could be, what life might look like, and where it might thrive. The search for water is far from over, and with it comes the promise of discovery, the thrill of the unknown, and the hope that the universe still has secrets to share. The great expanse of the universe is not just a backdrop for our existence, but a canvas where life itself may be painting its story, one hidden ocean at a time. What would it be like to walk on a world bathed not in sunlight but in orange haze? Could life, in forms entirely unfamiliar to us, exist on a moon so alien yet strangely reminiscent of Earth? Titan, Saturn's largest moon, challenges our imagination and stretches the boundaries of what we consider possible. For centuries, Titan was a shadowy enigma. Through telescopes, astronomers could glimpse only a faint golden glow, its surface hidden beneath a dense, opaque atmosphere. Its secrets were sealed in thick layers of nitrogen and methane clouds, an impenetrable veil that concealed a landscape no human had ever seen. What lay beneath? Mountains or plains, rivers or lakes, life or lifelessness? The questions lingered for decades, tantalizing in their mystery. Our first true glimpse came in the early 2000s, when NASA's Cassini spacecraft entered orbit around Saturn. Cassini's mission was ambitious, to study the planet, its rings and its moons in unprecedented detail. And Titan became one of its most captivating subjects. Then, in January 2005, a small probe separated from the spacecraft, Huygens, carrying humanity's curiosity directly to Titan's surface. The descent was slow, deliberate. Through thick orange clouds, Huygens pierced Titan's atmosphere, revealing a world both familiar and utterly alien. Below, frozen riverbeds carved through the icy landscape like ancient scars on a world of ice. Mountains, tall and jagged, rose in distant horizons, their peaks blanketed with methane frost. And everywhere, the ground was coated in a mixture of ice and hydrocarbon sand, creating a landscape both alien and eerily reminiscent of deserts on Earth. Titan is a world of extremes. Temperatures hover around 179 degrees Celsius, so cold that water is as hard as rock, and methane and ethane flow like rivers, fill lakes, and cascade in storms. Its skies are heavy with IT haze, scattering sunlight into an eternal twilight. Imagine standing on its surface, the ground crunching underfoot like frozen snow, lakes shimmering faintly in a pale light, and a sky tinged with orange, stretching endlessly overhead. It is a landscape of contrasts, a world at once foreign and strangely familiar. Titan's rivers and lakes are not made of water, but liquid methane. They carve valleys and channels, erode mountains, and feed vast seas of hydrocarbon, a cycle of precipitation, runoff, and evaporation, mirroring the hydrological systems of Earth. Yet the chemistry is entirely alien. Rain falls in methane droplets. Lakes ripple with liquid hydrocarbons. Even erosion, weathering, and sedimentation occur on a molecular scale, very different from the processes we know. But why does this matter? Why should we, so accustomed to water and oxygen, care about lakes of methane? Because Titan challenges our understanding of habitability. Life, as we know it, depends on liquid water. But Titan suggests that liquid, in other forms, may also create the conditions for chemistry to flourish, for molecules to assemble, and for the potential for life, alien yet possible, to emerge. Beneath its icy crust, models suggest a hidden ocean of water mixed with ammonia. This subterranean ocean is insulated from Titan's frigid surface, warmed by heat escaping from the moon's core. Could this hidden ocean harbor microbial life? Could chemical reactions in this dark, watery world give rise to life forms we cannot yet imagine? Titan offers not answers, but possibilities. And in these possibilities, our curiosity is endlessly renewed. The Cassini mission also revealed Titan's dynamic atmosphere. Seasonal changes driven by Saturn's long orbit produce methane storms, swirling clouds, and shifting dunes. The surface is not static, it is alive in its own way, shaped by wind, rain, and the slow dance of hydrocarbons. Dark, meandering rivers carve channels into icy plains. Giant dunes march across deserts sculpted by winds that have been blowing for millennia. And in the polar regions, vast seas, Kraken Mare, Ligeia Mare, and Punga Mare, glisten faintly, frozen and liquid liquid at the same time, a testament to a landscape sculpted by both chemistry and time. Huygens landing provided the first close-up images of Titan's surface, small pebbles of water ice, rounded by processes that could be familiar to an Earth geologist. Drainage channels, suggesting that liquid had flowed, perhaps repeatedly, over the surface, and horizons dotted with low hills, like mountains on our own planet. For the first time, humanity could see Titan not as a distant moon, but as a real, tangible place, a world waiting for exploration. Yet Titan is also a world of mystery. Its methane lakes are patchy and transient, filling in some regions while leaving others dry. Its surface hides changes over seasons. Clouds drift across valleys and dunes shift imperceptibly over decades. Each observation raises new questions. How stable are these lakes? What chemical reactions occur within them? Could they host life, even in a form utterly different from our own? Titan is not just a frozen moon, it is a laboratory of chemistry and climate. Its thick atmosphere allows complex organic molecules to form, molecules that rain down onto its surface, collecting in rivers and lakes. Methane becomes a solvent, nitrogen a shield. Energy from sunlight, rare but present, drives chemical reactions, while cosmic rays and Saturn's magnetic field introduce additional catalysts. In these extreme alien conditions, Titan shows us that life, or pre-life chemistry, may not be confined to Earth's warmth or water-rich oceans. It may be everywhere, waiting for the right circumstances to awaken. And as we reflect on Titan, we realize that it mirrors the larger questions of our exploration. Life elsewhere may not look like us. It may not breathe oxygen, drink water, or thrive in sunlight. It may exist in cold, dark oceans beneath ice, or in rivers of methane, or in clouds of organic haze. Titan teaches us to expand our imagination, to redefine habitability, and to accept that life may take forms as diverse as the universe itself. The Huygens landing, the images, the data, all of it invites us to wonder. What does it feel like to stand on a world where rivers are frozen methane, where skies are a perpetual twilight, where dunes march across deserts sculpted by wind and seasons alien to Earth? What chemistry, what processes, what mysteries are hidden beneath the ice? And what will our next missions, drones, landers, orbiters, reveal in the years to come? Titan reminds us that the universe is vast, strange, and beautiful. It reminds us that exploration is not only about discovery, but about imagination. That every new world we touch, every moon we study, expands not only our knowledge, but our sense of wonder. That life, in its many forms, known and unknown, may be closer than we think, waiting for the right conditions to flourish in the most unexpected of places. As we leave Titan's icy plains behind, we carry with us a sense of awe and possibility. We realize that the universe is not silent, not indifferent, but alive in its own ways, with rivers, lakes, clouds, storms, and chemical dances that may hint at life. Titan is both alien and familiar, a mirror reflecting our curiosity back at us, reminding us to look further, to imagine more boldly, to wonder endlessly. The mysterious landscape of Titan is a reminder that the universe still holds secrets, waiting to be uncovered. Where will the next journey take us? To the frozen seas of Titan, to Europa's hidden oceans, or to worlds yet unseen? The search continues, and with it, the hope that the cosmos may be far more alive than we ever dared to imagine. What does it mean to be alive? How resilient is life, really? Could organisms survive in worlds so hostile that they seem utterly inhospitable, where temperatures plummet, chemicals flow like rivers, and radiation strikes without mercy? For centuries, humans imagined life only in familiar places, warm, sunlit, water-rich environments. But Earth in its extremes has shown us otherwise. Deep beneath the Antarctic ice, in the crushing pressure of oceanic trenches, in steaming acidic springs, and inside radioactive rocks, life persists. Microbes, bacteria, archaea, and other extremophiles thrive where our instincts say survival is impossible. These remarkable organisms have expanded our understanding of what it means to live, challenging our assumptions and opening the door to imagining life beyond Earth. Consider thermophiles, microbes that flourish in boiling hot springs of Yellowstone, where water exceeds 90 degrees Celsius. They metabolize chemicals that would poison most life on Earth. Or psychrophiles, thriving in freezing Antarctic lakes, surviving where water is barely liquid and sunlight barely reaches. And then there are acidophiles and alkaliphiles, which make their homes in highly acidic or alkaline environments, extracting energy from minerals and chemical reactions rather than sunlight. If life can endure such extremes on Earth, what does that suggest for the rest of the cosmos? Could life exist on Titan, flowing through its methane lakes, metabolizing chemicals we consider toxic? Could microbes crawl beneath the Martian surface, shielded from radiation, surviving in pockets of briny water? Extremophiles have taught us that life is not fragile. Life is adaptable, creative, and unyielding. The search for life in extreme environments often begins with parallels on Earth. Hydrothermal vents in the deep ocean, for example, are dark, high-pressure, scalding habitats. Yet they teem with life, tube worms, giant clams, bacteria, forming ecosystems independent of sunlight. Chemosynthesis replaces photosynthesis, with organisms drawing energy from hydrogen sulfide and minerals rather than from the sun. Imagine a similar system beneath Europa's icy crust, warmed by tidal forces from Jupiter's gravity, with water and minerals interacting to create pockets of chemical energy. Could extremophile-like organisms thrive there, in the darkness, feeding on chemical reactions, isolated from the cosmos for millions of years? The possibility shifts life from being earthbound to a universal principle, adaptable and persistent, wherever conditions allow. Mars, too, offers tantalizing clues. Ancient riverbeds, dried lakes, and minerals shaped by water suggest that the red planet was once wetter, more hospitable. Even today, pockets of briny water may exist underground, protected from radiation and frozen temperatures. Could resilient microbes survive there, hibernating in ice, metabolizing when conditions allow? On Earth, microbes endure prolonged periods of dormancy in extreme cold, only to awaken when warmth and nutrients return. Perhaps Mars hosts life in this hidden, waiting state. On Titan, the challenge is different. Liquid water is nearly absent on the surface, replaced by methane and ethane. Yet even here, extremophiles may offer lessons. Organisms could theoretically metabolize hydrocarbons instead of water, using chemical energy from their environment, much like Earth's microbes exploit chemicals from rocks, vents, and ice. Life on Titan would be utterly alien, yet the principle remains the same. Survival in extreme conditions often requires innovation, adaptation, and resilience. Earth's extremophiles reveal another remarkable fact. Life often thrives in isolation. Microbes flourish in rocks kilometers underground, in saline lakes with no sunlight, in acidic pools where nothing else lives. They remind us that life is not dependent on comfort. It is dependent on opportunity. A niche, however small or hostile, may be enough. NASA and other space agencies have drawn inspiration from these terrestrial pioneers. Experiments simulate Martian soil, the icy surfaces of Europa, and the methane lakes of Titan to test whether microbes could survive. Some hardy species withstand radiation, vacuum, extreme cold, and chemical toxins, surviving months, even years. Each experiment demonstrates that life is more durable than we once imagined, and that the possibilities beyond Earth may be broader than we dared to dream. But how do these organisms survive such extremes? Extremophiles possess adaptations at the molecular level. Their proteins resist denaturation in heat or acid. Their cell membranes remain flexible in freezing temperatures. Some can repair DNA damaged by radiation or metabolize unconventional chemicals. Life adapts not by following our rules, but by creating its own, rewriting the playbook for survival. Consider Deinococcus radiodurans, a bacterium so resilient that it can endure radiation thousands of times higher than what would kill a human. Or halobacteria, thriving in hypersaline lakes where salt concentrations would desiccate most cells. And there are methanogens, producing energy from methane. Organisms that hint at the possibility of life in Titan's lakes or Enceladus's geysers. Each discovery expands our imagination and prepares us for a universe that may be teeming with life in forms we have yet to recognize. If extremophiles can survive beneath the Antarctic ice, in boiling springs, in highly acidic pools, or in radioactive rocks, what does that mean for our search for life elsewhere? The answer is both exhilarating and humbling. Life may not require Earth's exact conditions at all. It may thrive in darkness, in cold, in heat, in chemicals that would poison us, in isolation from sunlight and warmth. The universe may harbor life in ways our imaginations have barely begun to grasp. And yet there is wonder in the unknown. We have only scratched the surface. We have seen extremophiles in a fraction of Earth's habitats, and even that has revolutionized our thinking. Imagine what might exist on Europa, Enceladus, Titan, Mars, or on distant exoplanets orbiting stars we have yet to study in detail. Extremes once considered uninhabitable may in fact be the cradles of life. Could life survive beneath Europa's ice, in oceans warmed by Jupiter's gravity? Could Titan host hydrocarbon metabolizing organisms in its methane lakes? Could dormant microbes persist in Mars's subsoil, awaiting conditions that may never come? Each question invites us to expand not only our science but our imagination, challenging our very definition of life. And as we consider these possibilities, we must remember life is not fragile, it is resilient, inventive, and persistent. The story of extremophiles on Earth teaches us that wherever there is energy, chemistry, and opportunity, life may find a way. This knowledge transforms our exploration of the cosmos from a search for familiar conditions to a search for possibility itself. So we look outward to the frozen deserts, the toxic lakes, the subsurface oceans, and the alien skies. We ask not whether life will be like us, but whether life can exist at all. In forms adapted to the extremes, thriving where we thought survival impossible. And with every discovery, we realize the universe may be far more alive than we ever imagined. The extremophiles of Earth whisper a profound lesson. Life is not a fragile spark in the void, but a persistent flame, capable of surviving the unlikeliest of worlds. Could that flame burn elsewhere, on moons and planets beyond our sight? Could it thrive in the darkness, the cold, the alien chemistry of worlds like Titan, Mars, or Europa? The search continues, and in it we find not just answers, but wonder. Why are we alone? In the vast tapestry of the cosmos with billions of stars and countless planets, why have we yet to encounter another intelligent civilization? Could it be that life is rare or that intelligence is fleeting? Or is there a hidden barrier, a silent filter, that prevents civilizations from ever reaching the stars? This is the enigma known as the Great Filter, a concept that has both fascinated and unsettled scientists, philosophers, and dreamers alike. It suggests that somewhere between the emergence of life and the rise of technologically advanced civilizations, there exists a hurdle so formidable that few, if any, overcome it. To understand this idea, let us start with the Fermi paradox, named after the physicist Enrico Fermi, who famously asked, "Where is everybody?" With billions of stars in our galaxy alone, many older than our sun, the odds of intelligent life seem high. Yet, despite decades of searching, we have no confirmed evidence of extraterrestrial civilizations. No signals, no megastructures, no whispers from the stars, only silence. The Great Filter may explain this silence. Perhaps life itself is extraordinarily rare. Perhaps simple life is common, but complex, intelligent life is almost impossible. Or perhaps civilizations invariably self-destruct, wiped out by nuclear war, climate collapse, or the unintended consequences of their own technology. Consider our own history. Humanity has existed for only a tiny fraction of Earth's age, and yet we have developed technology capable of both exploration and destruction. Could this stage on the threshold of interstellar communication be one of the most dangerous in a civilization's lifetime? Are we, perhaps, perched at the edge of the Great Filter, facing trials that no other species has survived? The Great Filter could lie behind us, in the steps that brought life to complex intelligence. The emergence of single-celled life may have been extraordinarily rare. The leap from prokaryotes to eukaryotes, or from simple multicellular life to complex animals, may itself be a filter that few life forms surpass. Perhaps life elsewhere is trapped at the microbial stage, flourishing silently in oceans or beneath icy crusts, but never advancing to civilization. Or perhaps the filter lies ahead of us, waiting as a universal checkpoint that no civilization survives. Technological societies may inevitably encounter self-destruction through environmental collapse, nuclear war, or artificial intelligence run awry. The very tools that allow a species to reach for the stars may also contain the seeds of its downfall. This raises a profound, unsettling question. If the Great Filter is ahead, how far have we already traveled on this treacherous path? Have we overcome the improbable steps of evolution? Or are we still facing a challenge so great that most civilizations never survive long enough to communicate across the stars? Scientists and futurists have explored these possibilities in both theory and observation. Consider the search for extraterrestrial intelligence, or SETI. Decades of scanning the skies for radio signals have yielded nothing. The silence may not indicate the absence of life entirely, only the absence of civilizations that can and want to communicate. Perhaps intelligent life is widespread, but civilizations are scattered, isolated, or ephemeral, vanishing before we can detect them. And yet, there is hope in our understanding of the cosmos. Missions like Kepler and TESS have revealed thousands of exoplanets, some in the so-called habitable zone where liquid water might exist. Moons like Europa, Enceladus, and Titan harbor subsurface oceans, suggesting that life could thrive even in the harshest conditions. These discoveries remind us too that life may be common, but intelligent life, capable of building civilizations, may remain rare. The Great Filter challenges us to confront both cosmic and human perspectives. It asks not only why we have not met others, but also whether we ourselves will survive long enough to explore the galaxy. Are we the exception, a rare spark of intelligence against a backdrop of silence? Or are we part of a vast, unseen multitude of civilizations that never reach out before vanishing? Some theorists suggest that discovering simple life elsewhere could be dangerous in its own way. If we find microbial life on Mars or Europa, it might imply that the Great Filter is ahead, not behind us. Intelligence, then, would remain the rare and fragile outcome of a universe filled with life that never advances. The weight of such a possibility is humbling, but the Great Filter also inspires reflection. It reminds us that life in any form is precious. Humanity may not yet know how to avoid the hurdles that lie ahead, but we do have the awareness to act, to protect our planet, to develop technology responsibly, and to seek understanding beyond our world. Awareness itself may be our first step towards surviving the silent barrier. Philosophers, scientists, and dreamers have pondered the implications for centuries. Are we the universe's rare miracle, or merely one experiment among many, struggling to survive? Are we at the threshold of greatness or the precipice of oblivion? Every choice we make, every discovery we pursue becomes part of this cosmic story. In imagining the Great Filter, we also imagine possibility. If civilizations can survive, if intelligence can thrive, then the universe is not silent by necessity, but by chance, waiting for us or others to reach the stars. Our quest for understanding, for connection, and for exploration may be what allows us to pass through this barrier. Perhaps the silence is temporary, a cosmic pause. Perhaps other civilizations exist, separate, tethered from us by time, distance, or the limits of perception. And perhaps with patience, courage, and wisdom, humanity can endure long enough to hear the faint echoes of life elsewhere, or to become the voice that others far away will one day detect. The Great Filter is not just a scientific hypothesis, it is a mirror. It asks us to examine our fragility and resilience, our ingenuity and hubris. It reminds us that the universe is vast, indifferent, and challenging, yet filled with potential. In that silence, we hear not only the absence of others, but also the urgency of our own story. Where does the Great Filter lie? Behind us, in the improbable steps of evolution, ahead of us, in the trials that civilizations must face? Or is it both, a series of thresholds that test life's resilience across space and time? The questions remain unanswered, but they ignite our curiosity and propel us forward. As we gaze at the stars, we must remember that every discovery, every effort to reach beyond our world is an act of courage, a testament to life's capacity to strive, endure, and imagine. The universe may be quiet, but our journey continues, and perhaps one day the silence will break. What lies beyond the horizon of our current understanding? How far can humanity reach in its quest to know the cosmos? The future of space exploration is not merely about technology, rockets, or distant planets. It is about our enduring curiosity, the drive to uncover the unseen, to ask the questions that have echoed through human history. Are we alone? What other forms of life, intelligence, or wonder might exist among the stars? For centuries, we have looked up at the night sky with awe, tracing the constellations, imagining other worlds, and pondering the vast emptiness beyond. From the earliest astronomers charting the movements of planets to the first probes that carried human ingenuity beyond our fragile atmosphere, each step has brought us closer to the unknown. In the 20th century, our reach extended from the blue skies above to the moon's silent surface. Apollo astronauts left footprints in lunar dust, evidence of humanity's ability to step beyond its cradle. But as monumental as these achievements were, they were only the beginning, the first chapter in a story that continues to unfold across the solar system and beyond. Today, our exploration is no longer limited to the familiar. Robotic pioneers like Curiosity and Perseverance traverse the Martian plains, analyzing rock, soil, and ancient riverbeds, seeking the fingerprints of a planet that may have once harbored life. Each wheel mark in the red dust is a trace of human curiosity, a testament to our willingness to ask profound questions of distant worlds. And yet, Mars is just the beginning. The icy moons of Jupiter and Saturn, Europa, Ganymede, Enceladus, and Titan beckon with their frozen oceans and mysterious chemistry. Beneath kilometers of ice, vast subsurface seas may conceal conditions suitable for life. Europa's ocean is warmed by tidal forces. Enceladus vents plumes of water and organic compounds into space, and Titan's methane lakes create a landscape both alien and strangely familiar. Each mission that reaches these moons carries with it not just instruments and sensors, but hopes. The hope of discovering life, of understanding that the story of biology is not unique to Earth. With missions like Europa Clipper and the proposed Dragonfly drone to Titan, we will soon study these worlds in unprecedented detail, sampling atmospheres, mapping surfaces, and probing oceans beneath ice. Imagine descending toward Europa's icy crust. The sun is a distant pale light filtered through a haze of frozen vapor. Beneath, a liquid ocean churns, warmed by the gravitational dance with Jupiter, teeming with chemical potential. Could microbial life swim in these dark waters, adapted to pressures, cold, and chemical energy in ways we can barely imagine? And if life exists here, how might it have evolved differently than on Earth? Titan, with its orange haze and hydrocarbon seas, presents another kind of wonder. Its rivers and lakes are not of water, but of liquid methane and ethane. Storms sweep across its plains, carving valleys in ice as rivers of methane flow beneath the alien sky. Could life here exist, not as we know it, but in forms adapted to chemistry alien to our own? The mere possibility challenges our assumptions about what it means to be alive. Beyond our solar system, the discoveries of thousands of exoplanets have opened the door to new possibilities. Telescopes like Kepler, TESS, and soon JWST, the James Webb Space Telescope, allow us to detect atmospheres, search for biosignatures, and identify worlds in the habitable zone where liquid water could persist. Planets orbiting distant suns, some rocky, some gaseous, some bathed in the warmth of two stars, each as a potential home or a mirror of Earth's past and future. The future of space exploration is also a human story. Private companies, international collaborations, and visionary scientists are expanding our reach. Rockets will carry humans back to the moon, to Mars, and eventually beyond. Space habitats, fusion propulsion, and advanced robotics may allow us to venture where few have dreamed. But with each technological advance comes profound responsibility to safeguard life, to respect unknown ecosystems, and to ponder the ethics of exploration. We are standing on the threshold of a new era. The decisions we make now about sustainability, stewardship, and scientific inquiry will determine how humanity navigates the cosmos. Will we become a species that spans worlds, connected not just by technology, but by curiosity, wonder, and a shared desire to understand our place in the universe? Or will we remain bound to a single planet, dreaming of what lies beyond without ever reaching it? In the next decades, missions will delve into the chemical signatures of distant atmospheres, probe icy moons, and return samples from Mars. Instruments will detect the faintest glimmers of organic molecules, the subtle shifts in planetary climates, the whispers of oceans beneath ice. Each discovery will reshape our understanding, challenging what we know and inviting new questions. Could we one day detect life beyond Earth? Could a probe or telescope reveal a biosignature, the unmistakable mark of metabolism on another world? Could a human or robotic explorer glimpse a living ecosystem beneath Europa's ice, or a chemical dance of life in Titan's methane lakes? These questions are no longer science fiction. They are the horizon toward which we are moving step by step, mission by mission, observation by observation. And beyond the scientific, there is the philosophical. Space exploration forces us to confront the vastness of our universe. To consider the fragility of life and to embrace our own smallness. Yet it also inspires hope. Hope that we can survive the challenges of our home planet. Hope that we can extend life beyond its original cradle. Hope that our curiosity and ingenuity will carry us to the stars. The journey ahead is not just about discovery, but about perspective. Every mission reminds us that Earth is a singular oasis, delicate and precious. And every potential world we explore challenges our imagination. asking us to envision life in ways we have never known. From the first footprints on the moon to the oceans beneath icy moons, the future of space exploration is a story of courage, perseverance, and wonder. Where will the next discovery take us? Will we find life within our solar system or across the galaxy? Will we uncover ecosystems that challenge our definition of biology, or civilizations that reshape our understanding of intelligence? Each answer will bring new questions. Each revelation will expand the boundaries of human knowledge, and each mission will remind us that the universe is both vast and intimately connected to our own existence. As we look to the future, we are reminded that exploration is more than a journey through space. It is a journey of the mind and spirit. It is an affirmation that curiosity and courage are fundamental to life itself. And perhaps one day, the question of whether we are alone in the universe will be answered not with silence, but with the profound discovery that life in some form exists beyond our world. The stars await us. The moons, the exoplanets, the oceans beneath ice, the mysteries hidden in distant atmospheres, all of them call to us, whispering of the possibilities yet to come. Our journey into the cosmos is just beginning, and the future is boundless. As we reach for the stars, we are reminded that exploration is not merely about finding life. It is about understanding life in all its resilience, complexity, and wonder. The universe is waiting. And so, with every probe we send, every telescope we launch, and every dream we dare to pursue, we move closer to the greatest discovery of all, the realization that we are part of a story far grander than ourselves, a story that stretches across the cosmos and into the infinite possibilities of tomorrow.